Just as an inquiry, how well do you understand the problem we just did? Could you do it again? Okay, I like the maybe. I like the yes. Let's do another problem again, and then we'll find out if you can do it again, okay? So, just do another example problem. Here, I'm just gonna cut to the chase and try to finish this problem. In an appropriate amount of time. So, what we need to do here is, I'm gonna draw a picture. So, we're gonna go ahead and say, we've got this thing. We'll add a resistance here. This will be R1. We're gonna add a capacitance here. We'll go ahead and add an inductance like this that goes down here. We're going to add another resistance over here, and we're going to add another capacitance here. Because this is true enjoyment. You got it done already, Igor? Are you done yet? Oh, okay. I suppose I should give you numbers. I haven't given any numbers. I'm just being a jerk. Okay, so some numbers for the problem. We're going to say Vs is going to be equal to we'll say it's equal to 180 sine of 400t. Okay? We'll say R1 is equal to 8,000 ohms. We'll say C1 is equal to 50 microfarads. We'll say R2 is equal to, let's go with 12,000 ohms. We'll say C2 is equal to 80 microfarads. And we'll say L is equal to, I like 10 henries. Okay. And the question for this one is, what is P R2 RMS? How much power is being consumed by that second resistor? Nice. I'm going to go ahead and label nodes quick. Here we got node 1, node 2, node 3, node 4. Now, I drew this one a little bit confusing. If you need to draw the node flow diagram, or if you want to draw node voltage diagrams or whatever, you can. We know that, oh, we got another node. It's right here. It's node 5. My bad. So we know that Vs input, output node. The input node to Vs is 4. The output node of Vs is 5. For R1, the input node is 5. The output is 1. For C1, the input node is 1. The output node is 2. For R2, the input node is 2. The output node is 3. For C2, the input node is 3. The output node is 4. And for L, the input node is 2. The output node is 4. So the only real components that we can see in series right now are we have these two in series and we have these two in series. This is otherwise pretty gross. So, hard problem. That's why I'm doing it myself. All right. We could start with KVL and KCL if you really want to. Or we could not do that. Yeah. And then we could just calculate equivalent impedances and move from that direction. Which I think sounds a lot nicer to me. So let's do that. Okay, so I'm going to take this and I'm going to get an equivalent impedance. I'm going to figure out what the current is going out of the source, and then we'll work backwards through the system. Okay? So I'll identify the different circuits we're about to build. Circuit 1, we're going to combine this one and this one, this one and this one, because those are the ones that are in series. We'll just take the easy ones first. So circuit 1 is going to look like this. Doop, zoop, shoop, 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 and then we got shoop, 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 shoop. Okay, since we combined these two, we get rid of node 1. Since we combine these two, we get rid of node 3. So we have node 5 right here. We have node 2 way over here. And we have node 4 over here. Combining things in series means you remove a node. Combining things in parallel means you remove a loop. It's just how it works. So this is our first set of equations. Here we're going to call this ZEQ1. This will be ZEQ2. And there's just our L. Okay? So we know ZEQ1 is equal to, since they're in series, it's going to be equal to ZR plus ZC. 1. Okay? Okay. Nice. Get some good math going on. Yeah, there we go. Yes. Math. All right, what is ZR? That's ZR1. What is ZR1? Yeah. It's just equal to R1, which is equal to 8,000. What is the formula for ZC? There we go. We have one real component. We have one imaginary component. We don't have to come up with a phasor for this, just FYI. We never do. We can just keep going and things will become magical. I mean, I guess we could come up with a phasor if we wanted to, but well, let's not do more math. We don't need to. Okay, what is omega? Did I give you omega? What is omega? It's 400. So, all we have to do is just plug in R1 is equal to 8,000 minus 1 over omega is 400. C1 is 50 times 10 to the negative 6. Oh, excuse me. So doing that math, we got this becomes ZEQ 1 is equal to 8,000 plus 50i. Nice numbers, like that. Okay, and then we can do the same for ZEQ2. What does ZEQ2 equal to?
Minus KVL.
Yes. Yes, it would be. Thank you. Good catch. What is the formula for ZEQ2? Yes, it will be. Nice work. And that is just ZR2. The formula for that is R2. ZC2, the formula for that, it's the same formulas. 1 over omega C2 times I. R2 is 12,000. And then we know omega is 400. And then C2 is 80 times 10 to the negative 6th. So this ZEQ2 is equal to 12,000 minus 31.25i. Okay, so we've got that entire problem now figured out. Great. Now, do we have any components in series or in parallel? Okay, is it series? It's parallel, right? Which components are in parallel? These two, yeah, because they both start at the same node and end at the same node. Because of that, they're in parallel. So we can combine them in parallel. Okay, so second circuit that we're going to be building is going to look like this. I'm going to go ahead and bring this one up to the top just that it's not so gross. This is number 2. So here, this one is ZEQ1. This one right here is node 5. We do not get rid of any nodes because we're combining them in parallel. We're getting rid of a loop, not a node. So ZEQ goes between 5 and 2, ZEQ1. So this one is 2. 4. We only had 3? Oh, okay. And we'll go ahead and call this one ZEQ3. So what is ZEQ3 equal to? Oh, you know what? I need to actually give you the formula. These are in parallel. We have to use our parallel formulas now. So this actually ends up equaling 1 over ZQ2 plus 1 over ZL. My bad, sorry. Need to tell you these things before I ask them of you. So this is just because this is the parallel equivalence for our resistance formula. You've all seen this before. Series adds different than parallel. I'm going to write this a little bigger. There we go. And those are Z's, not 2's. Okay, so ZEQ 3 is equal to 1 over ZEQ 2 is equal to probably should have had to calculate that phasor, because it's hard to take a 1 over a complex number. So you know what, I'm going to take this, I'm going to figure out what the phasor is for these just real quick. So ZEQ1, the phasor is, it's not going to be a huge number. Yep, 8,000.2 times an angle of negative 0.358 degrees. And this one over here is equal to $12,000.0. 31.25 is a very small number compared to 12,000. And that's going to be an angle of almost 0. Yep, at an angle of negative 0.149 degrees. So if we go ahead and plug in 1 over 12,000 angle negative 0.149 degrees plus, well, 1 over ZQ, which is, when we calculate that one, oh, I guess you can plug in like 1s and J's. It's just gross. Yeah. Things are easier done in phasor form when doing division. So this is just equal to 1 over omega times L at an angle of, I think, 90 degrees. Yeah. So ZEQ3 is equal to 1 divided by 1 over, oh, gross, 1 over 12,000. So 0.0000833 at an angle of 0.149 plus, and then omega L is 400 times 10. It's 1 over 4,000 at an angle of 90 degrees, which is equal to 0.00025 angle negative 90 degrees. Okay? When you add up these two components, you have to take the sine and cosine function out of this one. You have to take, well, sine and cosine out of this one as well. And when we do that, we'll get some fun math. Still isn't super nice, turns out. Things in parallel suck. If somebody finds an easier way to do it in parallel, let me know. Okay, so ZEQ 3 is equal to 1 divided by 0.0000833 plus, well, that becomes a minus. I guess this becomes a plus. If you add in this piece, it's times 10 to the negative 7th. At that point, it's small enough we can ignore it. Because this one is times 10 to the negative 4th. I'm just going to ignore the sine piece out of this one and only take the cosine out because it's so close to 0. This one is close enough to 90 degrees that, well, it's only going to be in the I direction. So this becomes 0.00025I. If we combine those into one vector, this is ZEQ 3 is equal to 1 divided by 0.000264 at an angle of negative 71.57 degrees. Okay, so when we invert that, this becomes ZEQ3 is equal to 3788 at an angle of 71.57 degrees. So that was some gross math. Had to be done, but it was gross. And lastly, we add all of these in series. So our third and final system looks like this, where this is ZEQ 4, and it's just in series. So I'm going to go ahead and break this out into real and imaginary added together. So this becomes 3788 times cosine 71.57, and that's the real component, so 3788 times cosine 71.57. So it becomes 1198 plus then the sine of 71.57 is 3594I. Okay, and all that is that's just 3788 cosine 71.57 degrees and 3788 sine 71.57 degrees, and you multiply that one times I. Okay, so now that I have this, ZEQ4 is equal to ZEQ3 plus ZEQ1. So that is equal to 8,000 minus 50I plus 1198 plus 3594. So that is, whoop, I'll write out the formula. ZEQ1 plus ZEQ3 and that's equal to 8,000 minus 50I plus 1198 plus 3594I. We combine the 1198 and the 8,000, combine the reals, combine the imaginaries, and you get ZEQ4 is equal to 9,198 plus 3544I. Well, that's gross. Boy, that was a lot of math. Now we can take this, and this is, we'll calculate what the phasor is from this. So 9198 squared, 3544 squared, so this becomes 9857 at an angle of 21.07 degrees. Whew. Now we can find IS. I'm not going to erase anything yet, because we're going to need some of these formulas. Okay, so we know IS is equal to VS divided by ZR4. Okay. What is the phasor form of VS? It's 180 times the cosine of negative 90, so it's 180 at an angle of negative 90 degrees. Nice catch. Because I gave this to you in sine, the phase angle here has to be a negative 90, because sine is equal to cosine minus 90 degrees. There is no phi up here, otherwise it would be phi minus 90 degrees. If this was 400t plus 30, then your answer here would be negative 60 instead of 90, because it'd be 30 minus 90. Does that make sense? So that's the whole reason why Dylan told me the angle here is negative 90. You were on your game today. Doing great. Okay, so we take 180 and we divide it by that gross number over there. 98 57 at an angle of 20. What even is that?
1.07.
Oh, that's okay. Thank you. That was a degree sign, and it was like, it just looks like an alpha symbol. I can't read my own handwriting. It's awesome. Okay. So our IS value, we're going to calculate those two divided by each other. So I will do that. And this is equal to 0.01826. An angle of, here it is negative 90 minus 21.07. So that's at an angle of negative 111.07 degrees. Well, that's gross. Okay, now if we multiply IS by ZEQ 3, we can figure out what the voltage is between 2 and 4. That is the voltage across ZEQ 2. Okay? Once we know the voltage across ZEQ 2, then we can calculate what the current is through ZEQ 2 using the ZEQ 2 value, which will give us the current through R2. We multiply R2 by the current, and that's the answer. I don't really want to do all of that. Let's call it good because we calculated IS. So I'm going to go ahead and change the problem. P RMS of the source. So to calculate P RMS of the source, we're just going to multiply V RMS of the source times I RMS of the source, which is equal to 180 divided by the square root of 2 times 0.01826 divided by the square root of 2, which that is equal to 1.6435 watts. Yikes. So let's not do that more than we have to. Okay? I'm going to go ahead and give you a problem. And then I will give you your quiz and we'll be done for the day. Okay? All right. Problem I'm giving you. everything is going to be 100. Okay, can all work together. I'm going to shut off the stream, but I want you to try to solve that problem.